Hello everyone, welcome to my channel Sai Suriyas Academy. If you are new to my channel, then hit the subscribe button and press the bell icon for more interesting videos. In today's video, we are going to discuss about decimal to binary conversion. This can be done in two simple steps. First, you want to know about how to convert a decimal to binary as an integer part. In step 2, you want to know about how to convert a fractional part of a decimal to a binary number. Okay, these two methods has different types. That is, as an integer part, the conversion method is different, and for a fractional part, the conversion method is different. Now let's move on to the video. We all know that the decimal system consists of a base 10 number system, which consists of digits from 0 to 9. And in binary number system, it consists of base 2 number system, which consists of only 2 digits, zeros and ones. So now moving on to video, consider the example 981.25. This is the decimal number, given decimal number. Now we want to convert the decimal number to a binary number. In this, the 981 is considered as a integer part and 0.25 is considered as a fractional part. First we will solve the integer part, then I will explain the fractional part. Okay. Now in the integer part, consider the base idea is we have to continuously divide the decimal number by 2 till it reaches the minimum value zeros or ones. That is, after that we cannot be able to divide that number. It should reach a minimum value. The reminders has to be noted, and finally we have to write the binary number from the bottom to the top. This is the base idea. Okay, now we can solve it. Consider 981 when divided by 2. 9, 2 4s are 8, 1 remaining 18, 9. Again 1, it cannot be divided by 2, so 0 with remainder 1. Again divided by 2, 2 2s are 4, again 9, 2 4s are 8, 1 remaining, 1 and 0, 10, so 5, remainder 0. Again 245 has to be divided by 2. Now 30 is going to be divided by 2, which gives 15 with remainder 0. Again 2 7s are 14, so remainder 1. Again 2 3s are 6, remainder 1. Now till it doesn't reach a minimum 3, it can be divided by 2. So the final step, 2 1 2s are 2, remainder 1. So this is the final step. We had reached as a quotient 1 with remainder 1. Now it cannot be divided more since we reaches a minimum value zeros and ones. That is ones we have. So this number has to be written from the bottom to the top. Okay. This is the methodology for solving the decimal number as a integer part. Now, before writing the answer, let us solve the fractional part, and finally we can combine and write the answer for the given decimal number 981.25. Okay. The base idea for converting the fractional part is we have to multiply the number, that is the fractional part, by 2. Again, the integer part, the resultant, we get a result. In the particular result, we have to select and write the integer part separately, and again the fractional part has to be multiplied by 2. This process has to be continued. There arises a question when this process can be stopped. Suppose when the resultant, in the resultant fractional part, when it arises 0, after that we cannot be able to continue the process, so we can stop. For few numbers it can be attained in 1 or 2 steps, the fractional part as 0. In some numbers we cannot be able to attain, so at that time we can just make as a 3 iteration, a minimum 3 iteration. Okay. Now 0.25, this is the given fractional part. It has to be multiplied by 2, which gives 0.50. Here the integer part is 0 and the fractional point is 0.50. This is the integer part. So the integer part is noted here as 0. The fractional point 0.50 is again multiplied by 2, which gives the value 1.00. So here the fractional part attains 0. After that, we cannot continue the iteration because 0.00 into 2, the zeros will be goes on continuously. So we can stop the iteration. Suppose for different number, if we cannot attain a 0 0 in the fractional part, if the list goes on, then we can stop at 3 iterations. Okay. Now in this, the integer part is 1. So it is written here. Again the fractional part is 0 0. Since we attain the fractional part 0 0, we are stopping the iteration. And the numbers, that is the collected integer parts, has to be written from the top to the bottom. Now in this integer part, we had told that the result has to be noted from the bottom to the top. In the fractional part, the separated integers numbers has to be written from the top to the bottom. Now consolidating the result for 981.25. This is the given decimal number. So the values can be written as 1 1 3 4. 4 ones we have 1 2 3 4. Okay, 1 1 1 1. Again 0 1 0 1 0 1 0 1. Again 0 1. Okay. The numbers has been written from the bottom to the top as 1 1 1 1 0 1 0 1 0 1. This is for the integer part, and for the fractional part, it has to be written from the top to bottom. So 0.01. This is the resultant binary value for the given decimal number 981.25. So in this we have to remember 2 steps. When considered as the integer part, it has to be continuously divided by 2. The remainders has to be noted and the resultant quotient has to be written from the bottom to the top. Again for the fractional part, you have to multiply the fractional part 0.25 by 2. The iteration can be stopped when we reach as a fractional point 0.00. The integer parts, the resultant integer parts are collected separately and it has to be written from the top to bottom, and this is the final answer we had arrived here. In today's video, we are going to discuss about binary to decimal conversion. This can be done in 2 simple steps. In step 1, you want to know about how to convert an integer part of a binary number to a decimal number. In step 2, you want to know about how to convert a fractional part of a binary number to a decimal number. Now, let's move on to the video. In today's video, we are given an example binary number 10101101.1010. In this number, this first part is considered as an integer part, that is the numbers before the decimal point. And 1010, that is the numbers after the decimal point, is considered as a fractional part. Before that, the basics of binary and decimal, we all knew the basics, but still I will tell in short. The binary number system consists of base 2 number system, which consists of digits only zeros and ones. Only 2 digits are allowed here. In decimal number system, it consists of a base 10 number system, which consists of digits from 0 to 9. Now we want to convert a base 2 number system to a base 10 number system. So first I will explain the integer part, then we will move on to the fractional part. Okay. The numbers has been written here. This 1010, 1101 integer part and 1010 as the fractional part. Now for converting the integer part of a binary, in the positional number system, each binary digit has a weightage with respect to the base 2 number system. So for each digit, consider the last integer digit 1. Its weightage is 2 power 0. 0, 2 power 1. That is, the weightages with respect to 2 power 0, 1, the powers are increased from the right to the left for the integer part. You should remember this point. 2 power 0, 2 power n, and it continues till it comes the last number 1, which consists of weightages 2 power 7. Again, okay, let the fractional part remain as it is. Now first we will solve the integer part and later on move on to the fractional part. Okay, after adding the weightages, what we are going to do is we have to multiply the particular binary digit with the concerned weightage, and the sum of the products has to be found. That is the decimal number, the resultant decimal number what we want. So here for simplification, when a number is multiplied by 0, the value is 0. So I am marking all those zeros. no need to multiply and return and find 0 and add zeros, so the steps can be eliminated. So here 0, here 1 0, marking 2 ones, again 1 0. Till the integer part we are calculating just a small marking. Okay, the zeros are eliminated, and now we are going to write only the one value and the weightages to find the sum of products. So 1 into 2 power 7 plus 1 into 2 power 5. Here 0, so we are eliminating this. 1 into 2 power 5. Again a 0 we are eliminating. 1 into plus 1 into 2 power 3 plus 1 into 2 power 2. Again a 0 we are eliminating. 1 into 2 power 0. Okay, this is the integer part. Now the total is 1 into 2 power 7, which gives 128 plus 1 into 2 power 5, 32 plus 1 into 2 power 3, 8 plus 1 into 2 power 2, 4 plus 1 into 2 power 0. Any number to the power of 0, its value is 1. So 1 into 1, which gives 1. So the total value is 128 plus 32 plus 8, 32 plus 8, 40, 44, 45, 128 plus 45, which gives 173. This is the attained integer part. Now for the fractional part, we have to add continuously the sum of and find the sum of the products for the fractional part also. The base idea for converting a fractional part of a binary to decimal is we have to add the weightages similar as integer. But what happens is we have to add starting from the left to the right for the fractional part only, just remember. So 1010, and again the values has to be written as a negative powers. It has to be incremented as a negative powers. For first one, 2 power minus 1, this 0, 2 power minus 2, 1, 2 power minus 3, and 0, 2 power minus 4. Here the integer values are incremented starting from the right to the left for the integer part of binary, and for the fractional part the values are incremented with the negative power starting from the left to the right. So we can, this is the integer part. Now we have to find the, after adding weightages, we have to find the sum of the products. So 1 into 2 power minus 1. Again 0 we can eliminate here. Again one more 0 we can eliminate here. Okay, there is no need to represent the zeros multiplied and again adding zeros will give nothing. So 1 into 2 power minus 1 eliminating, 1 into plus 1 into 2 power minus 3. This can be added continuously till integer part, afterwards fractional part, plus till this we have completed 1 into 2 power minus 1, which gives 1 into 1 by 2. This can be calculated as plus 1 into 1 by 8. So for 1 into 1 by 2, its value is written as 0.5 plus 1 into 1 by 8, its value is written as 0.125. So when adding with the integers, the final value is, we have to add all the 173 plus 0.5 plus 0.125, which gives 173 plus this point values when added will give 0.625, which gives 173.625. This is the attained decimal number for the given binary number 1010.1101.1010. Now the base idea is you have to remember only 2 steps, that is each number has a weightage with respect to base 2 number system, and for the integer part conversion the binary numbers has to be, the weightages has to be added starting from the right to the left. And for the fractional part, the weightages has to be added as a negative numbers. It has to be incremented as 2 power minus 1, minus 2, minus 3, starting from the left to the right. Calculate all the multiply the concerned binary digit with the weightages, find the sum of products and find the final result. The sum of products has to be found both for the integer part as well as the fractional part. Add all those values and then the final value 173.625. This is the attained decimal value. Okay, that's all for today's video. In today's video, we are going to discuss about the decimal to octal conversion and then octal to decimal conversions. We had already discussed in the previous videos about the decimal number system and then octal number system and then binary hexa number systems. The decimal number system consists of numbers which has a base 10 and the numbers from 0 to 9. The octal number system consists of a base 8 and which has the numbers from 0 to 7. And today's video, we are going to talk about the conversions from decimal to octal. First, we can see the decimal to octal and then the octal to decimal conversions. And then as an integer part, what we have to do for conversion, and when we are having a fractional part, what we have to do, we can discuss in this video. The first example is, consider the decimal number 45796 to the base of 10. Here we have to convert this number base 10, that is the decimal number, to the octal number system. The idea behind this is we have to continuously divide this number by 8 and the remainders has to be noted. We have to continue this till it reaches a very minimum value of 1 or 2, that is which cannot be again divisible by 8 till it reaches to a minimum value, and then the remainders will be between 0 to 7 only, of course. So we have to continue till we reach the least number. Consider 45796 to the base 8. So when divided by 45796 to the base 10 decimal number, we have to convert it into octal. So first we are dividing it by 8. 5 8s are 40. Remainder 5 in 45. 57. 7 8s are 56. Remainder 1. Again 90. 2 8s are 60. Remainder 3. 36. 4 8s are 32, remainder 4. The remainder 4 is noted here. And then 5724 divided by 8. And then 89 when divided by 8. 1 8s are 8. Again in 9, 1 8s are 8, remainder 1. 11 which is divided by 8. 1 times 8 and then the remainder 3. Now how we have to write the answer is, we have to write from the bottom to the top. That's why the arrowhead is drawn like this. So we have to write 1 3 1 3 4 4. So 1 3 1 3 4 4. For this particular decimal number 45796 to the base 10, we have arrived the octal number as 131344 to the base 8. Now this is the integer part. When we are having a fractional part, how we can able to transfer or how we can able to convert it? For having a fractional part, we have to multiply that number by the 8 for converting to decimal to octal. So consider the number 0.015625. Okay, again one question arises, how many times we have to multiply those numbers by 8? When the fractional part arrives at 0.000, we can stop there, because with the fractional part we have to multiply by 8. We cannot able to continue. In some cases, we cannot arrive the solution as 0.000. At that time only, we can continue the iterations for 3 or 5 times. So first consider 0.015625 into 8. We will arrive a solution of 0.125. Here the integer part is 0 and then the fractional part is 0.125. So the integer part is written as integer 0. The fractional part 0.125. Again the 0.125 is multiplied by 8. So the fractional part when multiplied by 8, we reaches as 1.000. Here again the integer is 1 and the the fractional part is, we are arriving as 000. So what happens? We cannot able to continue the iteration with 0 when multiplied by 0. We will always return a 0. So we have to stop here. And how we have to write the answer is, we have to write from the top to the bottom. So for 0.015625 to the base 10, we are arriving a solution of 0.01 to the base of 8. Okay, that's all for the decimal to octal as an integer part and decimal to octal as a fractional part. Now consider octal to decimal. First we have to consider as a integer part. What we have to do is, the base idea is, we have to add the weightages depending upon the positions. That is from the least value, that is from the right to the left, we have to add the weightages as 8 power 0, 8 power 1, 8 power 2, 8 power 3. The powers are increased from the right to the left. So after the powers are added, we have to multiply with those particular digits, and the sum of the products has to be added at the last. So 5 into 8 power 3 plus 3 into 8 power 2 plus 2 into 8 power 1 plus 4 into 8 power 0. So 5. So this products arrives as 2560 plus 192 plus 16 plus 4, which gives an answer of 2772. So the particular for this octal number 5324, we have arrived the decimal value as 2772 to the base of 10. This is the method for considering octal to decimal in the integer part. If the same octal to decimal conversion as a fractional value, how we can able to convert is 215. Consider this example, 215.43. This point can be noted as octal 215.43. So when considering this point, that is the decimal value, we can have these values as, for 215, 8 power 0, that is from the right to the left for integer value, as considered in the example 1. For 5, 8 power 0, for 1, 8 power 1, for 2, 8 power 2. Here we are having a decimal point. Here we are having a decimal point. So for representing this 4 and 3, point 4 and 3, the weightages can be added as starting from the left to the right, which 8 power minus 1 and 8 power minus 2. The negative values will be keep on increasing from the left to the right as 8 power minus 1 and 8 power minus 2. Again we have to multiply all those weightages with the particular digits with the weightages with the base 8, and then add all those products, we will get the final answer. So finally adding the integer values 128 plus 8 plus 5, we arrives as 141, and then 0.5 and then 0.0469, we arrives as 5469, and then the final answer is 141.5469 to the base of 10. Okay, this is the octal to decimal value when we are having a fractional point. When we are having an integer point, this is the example, and when we are having a fractional part, this is the example. A small work for you: find the 0.16 to the base of 10 and convert it into to the base of 8, that is to octal, decimal to octal. In this example, 0.16, you will not get the 0.000 as in this example. So you can either convert for 3 iterations or you can stop at 5 iterations. That is your own wish. And then next, find another small work, 325.12 to the base 8, convert it into the decimal value and write all those values in the comment section. And that's all for today's video. In today's video, we are going to talk about 2 types of conversions. That is decimal to hexadecimal and hexadecimal to decimal. We all know that the decimal system consists of digits 0 to 9, whereas in the hexadecimal system, it consists of digits from 0 to 15. Whereas 0 to 9 numbers are represented as it is as 0 to 9, and numbers from 10 to 15 are represented by alphabets such as hexa 0 to 9 as it is 0 to 9, and from 10 it is represented as, for 10 it is represented as A, 11 as B, 12 as C, 13 as D, 14 as E, and 15 as F. First now consider the decimal to hexadecimal part. Consider a first example, very small example, a number 10 to the base of 10. When it is at 10, it can be directly represented by A, the alphabet A. So 10 of base 10 is represented by A of 16. Consider another example, 7562 to the base of 10. Now we want to convert it to hexadecimal conversion. For the continuously we have to divide by 16 and the reminders has to be noted. Consider 7562. Again in 29 when dividing by 16, 1 16s are 16, remaining 13 which is represented as D. Now after calculating the reminders, after the division is completed, the reminders has to be noted from the bottom to the top. So it can be written as 1, 13 is represented as D alphabet. So 1D8A. So 1D8A to the base of 16. This is the decimal to hexadecimal conversion. Now this is an integer part. When we are having a fractional part, how we can able to convert it? So decimal to hexa fraction. Consider this decimal number 0.00390625 to the base of 10. The base idea here is we have to multiply the particular number, fractional number, by 16. Since we want to convert it into hexadecimal, so we have to multiply by 16. The quotient what we are getting, again the integer number is noted and again the fractional part is again multiplied by 16. So it can be continued. How many times we can able to, or we have to do this calculations means till it reaches 0. When the fractional part reaches 0, we can stop here. In some cases, we cannot reach the 0. So at that time, we can calculate for just for 3 iterations or 5 iterations, we can stop. When it is goes on without reaching 0, we can stop there. So the first step is 0.00390625 into 16, which gives 0.0625. Here the integer part is 0, that is the number before the decimal point, and the number after the decimal point is called the fractional part. So the integer is noted as 0 and then 0.0625 into 16. The fractional part is again multiplied by 16. Here we are reaching value as 1. With integer part as 1 and the fractional value as 0. When we reach the fractional part as fully continuously 0, we can stop here because we are going to multiply for the next iteration. We have to multiply the fractional part by 16. That is the 0 into 16. So continuously we will be reaching the 0 value only. So when we reach 0, we can stop here. And then again the values, integer values noted here has to be written from the top to bottom. 0, 1. So it is written as 0.01 to the base of 16. That is the decimal to hexadecimal with the fractional value. So now we had discussed about decimal to hexadecimal, integer part and as a fractional part. Now we have to calculate we are going to know about the hexadecimal to decimal. When the number is given in the hexadecimal, we have to now convert it into the decimal format. So consider the same example. In the first example, we had discussed about 7562 decimal number in which we had reached the answer as 1D8A. So for your clarification, I am taking this 1D8A, that is the base 16 number, and I am going to calculate it to the decimal number. So 1D8A, it is taken. This is the integer part. And the weightages, the idea here is the weightages has to be added. That is the number belongs to hexadecimal. So it is of base 16. And with the base 16, starting from the right side to the left side. Starting from the right side to the left side, we have to add the weightages. That is for A, first we have to consider 1D8A. For A, it is represented as 10. For 8, it is 8. For D alphabet, the particular digit is 13. For 1, it is 1 as it is. After writing the numbers, the weightages can be given. That is from the right to the left. So, for the 10, it is assigned as 16 power 0. And the powers will be increasing when we are moving from right to left. So, for 8, 16 power 1. For 13, 16 power 2. For 1, 16 power 3. So, after adding the weightages, the digits, particular digits has to be multiplied by the weightages and the sum of the products can be found there. So adding all those numbers, we reach the value 7562, which is the decimal value. 7562 we had calculated and we arrived 1D8A, and similarly for the hexadecimal 1D8A, we have arrived the decimal value 7562. That is the same value we had arrived here. So for the integer part, it is calculated. So now considering the decimal part. That is the fractional part. When we are having a fractional part, how the weightages can be added. A slight alterations can be done. That is the number, consider the number 4A9.2B. When the alphabets has been come, so we have to make the particular, that is represent the particular numbers or the digits, concerned digits. So for B, it is represented as 11. For 2, it is 2. For 9, the number same 9. 0 to 9, there are no changes. For A, it is represented as 10. For 4, it is 4. So after writing these numbers, we are going to add the weightages. So for the integer part, as we had already discussed, before the decimal point, it is considered as the integer part. The weightages are added from the right to the left. That is starting from 9. For 9, it is assigned as 16 power 0. For 10, 16 power 1, and 4, 16 power 2. That is the powers keep on increasing from the right to the left. Then what about the fractional part? The values will be increasing from the left to the right by terms of negative powers. That is, 2 is represented by 16 power minus 1 and 11 is represented by 16 power minus 2. Suppose if we have some other digits here, the powers will be moving on increasingly in the negative values as 16 power minus 3 and minus 4 and so on. So now the weightages are given and then we have to the particular digit or the number has to be multiplied with the given weightages and the sum of the products has to be found here. So and then again adding all those values, 1024 plus 160 plus 9 plus the decimal values, which gives the values as 1193.1679. So for the particular number 4A9.2B hexadecimal number, we have arrived at the decimal value as 1193.1679 to the base of 10. So these are all the things we had discussed here. And finally a small work. Find for the hexadecimal value, convert it into the decimal value. That is AB21.34 to the base of 16. Convert it into the decimal value and write the answer in the comment section. Okay, that's all for today's video. Thank you for watching my video. In today's video, we are going to talk about binary to octal conversion. Previous videos we had discussed about so many number conversions such as decimal to binary, decimal to octal and decimal to hexa. Now we are going to discuss about binary to octal conversion. Binary consists of base 2 number system, which consists of only zeros and ones, whereas octal consists of base 8 number system and the numbers which are used in octal is 0 to 7. Only 0 to 7 is represented in the octal number system. Now for this conversion, we are going to discuss about two types of methods, that is two methods. In the first method, the base idea is we have to convert the concerned binary number to a decimal number. When it is converted to decimal number system, it is easy to convert to a octal number system. So for converting these methods, we have to add weightages. For converting a binary number to octal, we have to add weightages and find the sum of products. And then in the second method, as we had already discussed, as octal number is represented by a 3-digit binary, 3-digit binary. Suppose for example, for 0 it is represented as 000, for 7 it is represented as 111. So by using this, the particular binary, this is called the grouping method, the particular binary value is grouped by 3 bits and the equivalent octal value is found. Now let us see about the first method. In the first method, consider an example 100101110. It is an integer number, that is, it does not contain any fractional value. So the weightages can be added starting from the right end to the left end. And the powers will be keep on increasing, such as 2 power 0, 2 power 1, 2 power 2 till 2 power 7. And then the particular digit has to be multiplied with the weightages, that is 1 into 2 power 7 plus 0 into 2 power 6 plus 0 into 2 power 5 plus 1 into 2 power 4 plus 0 into 2 power 3 plus 1 into 2 power 2 plus 1 into 2 power 1 plus 0 into 2 power 0. Adding, we arrive the answer as 150, which is to the base of 10. Now we had arrived to a decimal number system. After converting to decimal number system, we have to change it into octal conversion. For converting to octal, the particular decimal number system has to be continuously divided by 8 till it reaches a minimum value, and the reminders are noted, and the answers has to be noted from the bottom to the top. 2 to 6, which is the concerned octal value, 2 to 6 to the base of 8. This is the first method. Now consider the second method called the grouping method. That is, in the grouping method, we have to find the octal digit, the equivalent, binary equivalent. So here we have written the binary equivalent values for 3 digits. Suppose if you have a doubt how the decimal value or the octal digit has to be converted to decimal, just for example 7 I am representing, how this value 111 comes. 7, which is to be divided by 2. 3 times of 2 3s are 6, remainder 1. Again when divided by 2, 1 times 2, remainder 1. It has to be noted from the bottom to the top, which is equivalent to 111 to the base of 2. 111. Similarly for other digits, you can now calculate on your own. So these are the binary equivalent values. In the grouping method, consider the same example what I had taken here in the first method, that is 100, 10, 110. So consider 100, 10, 110. Now how we have to divide is, starting from the right hand side, since it is the integer number, how the weightages are added. Similarly, starting from the right hand side, we have to divide these binary bits into 3 group of bits. From the last 0, 1, 1. So 110 is grouped. Again 0, 1, 0. So 0, 1, 0 again grouped. Again here we are having, after grouping, only 1 and 0. Here we are not having 3 binary digits. Only 2 digits we are having, 1 and 0. So here another 0 can be added. Here we are adding another 0. So it becomes 0, 1, 0. And then the equivalent octal value can be found here. So for 0, 1, 0, it is 2. Its value is 2. Again 0, 1, 0, its value is 2. Again for 1, 1, 0, it is 6. So the value 6 is represented. So the concerned octal digit is 2 to 6 to the base of 8. That is the answer we have got here in the first method. By grouping method, simply we can directly convert from the binary to the octal conversion. The same answer we are getting. And then next, in the second method, grouping method, with the fraction, how we can able to convert it into octal conversion. Consider an example, 111.0011.1011. For integer grouping, I had already stated that starting from the right to the left, we have to group the bits by 3 bits. So here 0, 1, 1. Again 1, 1, 0. Again we are left with only single digit 1 here. So when we are left with a single digit, we have to change it into 3 binary digits. So zeros are added before the 1. 0, 0, 1. These 2 zeros are we are adding to convert it into a 3-bit binary digit. So 0, 0, 1 added here. This is the integer part. Now consider the fraction part. Here we are having 1011. For fractional part, we have to divide the bits into 3, starting from the left to the right. So 1011, first 101, which is grouped here. Again 1 is left here. So 1 is, we have to convert it into 3 binary digits. We are having only single one. So 2 zeros are added here, which makes us 100. I hope you can understand here. When converting, here we are left with only 1. So 2 zeros are added in the left hand side. Again for the fractional part, here we are adding 2 zeros at the right hand side for converting it into a 3 binary digit. So for 001, which is represented as 1. 110, which is represented by 6. For 011, its equivalent value is 3. The binary value for 011, equivalent value is 3. 101, the equivalent value is 5. 100, its equivalent value is 4. 101, 5, 100, its equivalent value is 4. So the concerned for 3-digit binary equivalent, the concerned octal value is found here, that is 163.54. So that is the concerned octal value here. Now a small word for you. Convert 110011.1010 to the base of 2 to the octal number system. Consider this fraction binary digit and convert it into octal and write it in the comment section. That's all for today's video. Keep supporting Sai Suriyas Academy. We'll meet you in next video. Thank you. In today's video, we are going to discuss about the octal to binary conversion. Here we are going to discuss about two methods. Two types of methods we are going to discuss here. The first method consists of converting the octal to decimal number system, and after converting to decimal number system, we have to convert it into the binary number system. The second method, a very simple method, consists of direct substitution of the binary value. Each octal digit has a equivalent binary value. We can be able to substitute those values. So in today's video, we are going to discuss these two methods. Let us move on to the first method. When considering octal, it consists of base 8 number system and the digits from 0 to 7 are only allowed. 8 and 9 are not allowed here, only 0 to 7. The numbers are allowed. And when consists of binary number system, it consists of base 2 number system. So in which only zeros and ones are allowed. Other numbers are not allowed. So from a base 8 number system, how it can be transmitted to base 2 number system, how it can be converted to base 2 number system. Now consider an example 205 to the base of 8. First we have to convert it into the decimal number system. For converting to decimal number system, we have to assign the weightages starting from the right side to the left side. The weightages can be assigned with the base 8 value, and the weightages will be keep on increasing. Just consider for 5 it is assigned 8 power 0, for 0 8 power 1, and for 2 8 power 2. We are considering the example 205 to the base 8. After the weightages are given, it has to be multiplied by the particular digit and the sum of the products has to be found. So 2 into 8 power 2 plus 0 into 8 power 1 plus 5 into 8 power 0. So 2 into 8 power 2, 2 into 64, 128 plus 0, 0 into 8 power 1, 0 plus 5 into 8 power 0, 5, which gives 133 to the base of 10. Now we are in need of the binary number system. So from decimal to binary, we have to transfer it from decimal to binary. For that we have to divide that number continuously by 2 and the remainder has to be noted till it reaches the division has to be continued till it reaches a minimum value 1 or 0. And after that from the bottom to the top the quotient has to be noted. Let us see. We have to write the quotient from the bottom to the top. So the final answer is 1, 1, 2, 3, 4, 4 zeros, 1, 0, 0, 0, 0, again 1, 0, 1 to the base of 2. So for the example 205 to the base of 8, we had converted it into decimal system, and from the decimal system we had converted to binary by dividing by 2, and we had reached the final answer like this, which consists of only ones and zeros. This is the first method. Now we have to move on to the second method, a very simple method. Consider this table. It consists of octal digits 0 to 7. On the concerned binary values are represented here. Octal, always a octal digit is represented by a 3-digit binary. That is for 0, 0, 0, 0, for 1, 0, 0, 1. 3-digit binary value for 7, 1, 1, 1. It is represented. So by substituting these values directly, we can attain the answer in the second method. Consider the same example 205 to the base of 8. The first example what we had considered. Here the 205 to the base of 8, we are going to assign the values directly. Substitute the direct 3-digit binary values. That is for 2, we are assigning 0, 1, 0. For 0, 0, 0, 0. For 5, 1, 0, 1. So here the first digit is 0, so we can discard it. So writing starting from here 1, 0, 0, 0, 0, 0, 0, 0 here, and then 1, 0, 1, 1, 0, 1, which is the same answer what we had attained here. So the first method and the second method yield the same result. Then consider another example with a fraction value which consists of a fractional value 367.542 to the base of 8. So when considering 367.542, again we have to represent the values concerned directly, that is the concerned binary values. For 3, 0, 1, 1. For 6, 1, 1, 0. For 7, 1, 1, 1. For 5, 1, 0, 1. For 4, 1, 0, 0. And then for 2, 0, 1, 0. And then we have to segregate all those values and write the answers. Here the first digit is 0, hence it is discarded. So 1, 1, 1, 1, 0, 1, 1. And then after the decimal point, here also the same decimal point can be represented. For 5, 1, 0, 1. For 4, 1, 0, 0. For 2, 0, 1, 0 to the base of 2. So that is the final answer. So today we will consider work for you, right? (132.11) to the base of 8, convert it into binary value and write in the comment section. Okay, that's all for today's video. Keep supporting Sai Suriyas Academy. Thank you. In today's video, we had already been discussing the number system conversion. In this series, in today's video, we are going to discuss about the binary to hexadecimal conversion. We all know that the binary system consists of only zeros and ones, and it consists of a base 2 number system. Whereas the hexadecimal, it consists of digits from 0 to 15 and it contains base 16 number system. So, what is the methodology to be followed for converting binary to hexadecimal? Here we are going to discuss about two types of methods. That is for integer method and for a fractional method. In the integer method itself, we have two types of methods. One method is the first method is we have to convert the binary to the decimal number system, and then again from the decimal number system we have to convert it into the hexadecimal number system. And the second type method consists of converting directly from the binary number to the hexadecimal using a grouping method. We can see these two methods one by one. Consider the first method. Consider an example 1100,101. The basic idea here is we have to convert it into the decimal. First we have to convert it into the decimal and then we have to convert to hexadecimal. For converting to decimal, here since it consists of base 2, we have to add the weightages starting from the right to the left. So the first digit 1, 2 power 0 is assigned, 0 2 power 1, 1 2 power 2, 0 2 power 3, 0 2 power 4, 1 2 power 5 and finally 1 2 power 6. After the weightages are added, we have to multiply with the concerned digits and the sum of the products has to be found. So the total sum is 101 to the base of 10. Now we had attained the decimal value. After getting the decimal value for converting to hexadecimal, the idea here is we have to divide this number by 60 until it reaches a minimum value. The remainders has to be noted and the final value has to be written from the bottom to the top. So consider 101 and divide it by the 16. So when dividing by 16, 6 16s are 96 and the remainder is 5. So we have to write from the bottom to the top. So 6, 5. The remainder 5. It is noted as 65 to the base of 16, which is the attained hexadecimal value. This is the first method. Now we are going to see about the second method, that is the grouping method. How the numbers can be grouped so that it can be attain a value. We all know that the hexadecimal number system, when it converts to binary, or it can be represented in a binary number system by 4 digits numbers. Consider this table. 0 is represented as 0000 till it attains 15. From 10 it is represented by alphabets. 10 to 15 is represented by A to F. 10 is represented as 1010 and 15 represented as 1111. We all know this table already. Suppose if it doesn't know how to make this table or how to convert, just convert by dividing the number by 2. Consider a small example. 2 divided by 2, 1, 0. Write it from the bottom to the top, 1, 0. Since we are representing it by 4 digits, it can be represented as 0, 0, 1, 0. Similarly, for all the other numbers you can find. If you can't remember the table, just you can do on your own. Now, about the grouping method, how we can able to divide the numbers, we can see now. Consider the number, the same example what I had taken here in the first method, 1100 101. 1100 101. Here the numbers has to be grouped by 4 binary digits to convert to hexadecimal. So starting from the right to the left. So starting from the right to the left, the numbers has to be divided as 0101 and 110. So we want to change it into hexadecimal. So we need 4 binary digits. So here it is represented 0101, the first 4 binary divided digits, and then again 110. So we want to, when you want to change to hexadecimal, we have to have 4 binary digits. So a 0 is added before here. This 0 we have to add. Since we have 3 binary digits, this 0 has to be added. After adding 0, the values can be converted. So 0110, 0110 here represents 6. It is noted. 0101, it is represented as 5. It is noted here. So 65 to the base of 16. So the answer what we had got in the first method, that is by converting to hexadecimal and then to, by converting to decimal and then to hexadecimal, we had attained 65. Here by grouping method, we had attained simply the answer as 65 using this grouping method. Consider the next example, grouping with fraction. When we have this is for the integer number. When you have a fractional number, how grouping can be done? Here there is a slight modification here. So when considering the integer number, we had already stated that from the right to the left, the numbers has to be grouped. What about the number that is the fractional number? The numbers can be grouped starting from the left to the right. That is here this number can be grouped as 1, 2, 3, 4. Just for your representation I am doing here 1100, 4 digit here. And then here starting from the left to the right 1101, 1101, 01. So when representing 0010, 0011, here we are left with 11. So in order to convert to hexadecimal, we need 4-digit binary. So for 11, here we are adding these 2 zeros. So it is, we can have now as 0011. Similarly, in the fractional part also, after converting 1101, 1101, here we are left with 2 digits 01. So in this portion, a 00 can be added here to convert it into 4-digit binary. So 0100. So now we have all the partition has a 4-digit binary. So when 4-digit binary, using this table you can convert here. You can either use this table and convert, or you can use this simple method by adding weightages and you can find the value when you can't remember this table. So consider 0011, 0011 it represents 3. Again 0011 it represents 3. 0010 it represents 2. 1101 it represents 13. 1101 represents 13. 13 has to be represented by the alphabet D. So again it is converted to D. Similarly 1101 13 value and it is represented by the alphabet D. And finally 01 we are left with 01 and 2 zeros are added here. So now the value becomes 0100 which represents the value 4. So 4 is written here. So the final value is 332.DD4. D is represented for 13. So DD4 to the base of 16. This is the final value. So today we had seen binary to hexadecimal with two methods, for integer number and for a fractional number. For the integer, okay, that's all for today's video. Keep supporting Sai Suriyas Academy. We had been discussing the number system conversion types, number system conversion series. In today's video, we are going to discuss about the hexadecimal to binary conversion. In the hexadecimal to binary conversion, we can use two types of methods. The first method is converting the hexadecimal to decimal, and from the decimal converting it to the binary conversion. This is the first method. And the second method consists of directly substituting we all know that the hexadecimal can be represented by a 4-digit binary value. By directly substituting the 4-digit binary value, we can convert it into the binary value. Then for integer type and with a fractional value, how it can be substituted, the examples have been discussed here. Now we first move on to the first method. Consider the example A5. We all knew that the hexadecimal consists of digits from 0 to 15, and from 10 to 15 it is represented by alphabets A to F. And each hexadecimal is represented by a 4-digit binary value. This is listed in the table here. So now when we want to convert this number A5, we want to convert it into the decimal system. For converting to decimal system, the idea here is we have to add weightages starting from the right to the left. Since we are having an integer value, the values can be substituted from the right to the left. So for 5, 16 power 0, for A, which is represented as 10, the value of A is 10. 60, for 10 it is substituted as 16 power 1, the weightage is added. Now after weightage is added, we have to multiply with the concerned particular digit, and the sum of the products has to be found. So 10 into 16 power 1 plus 5 into 16 power 0, which gives 160 plus 5, which gives 165 to the base of 10. Now we have arrived the decimal value. We want to convert it into the binary value. For converting to binary, the decimal number has to be continuously divided by 2 till it reaches a minimum value, and the reminders has to be noted, and finally the values has to be written from the bottom to the top. Consider 165 divided by 2. We had already discussed about so many times these type of conversions in the previous videos. I am directly representing the answers. So now the answer can be written as, starting from the bottom to the top, 10 10 0 0 101. So 10 100 101 to the base of 2. This is the binary value. Hexadecimal consists of base 16 and binary value consists of base 2, which consists of zeros and ones. So we are converting to decimal, and from decimal we are converting to binary. Now consider the second method. I am taking the same example A5. A5. For A it is represented as 10, and 5 it is as it is 5. So for A, consider the table. Each hexa number is having a 4-digit binary value. The table is represented here. We have 5. From the table we can directly represent 0 1 0 1. For A 10, it is represented as 1 0 1 0. So when writing 1 0 1 0 0 1 0 1 to the base of 2, the answer is same here, 1 0 1 0 0 1 0 1. So the same answer we are getting here. All numbers we can use this methodology. For large type of numbers, the second method is the best method to convert from hexadecimal to binary. Now the integer values is represented. Again consider an example with the fractional values. Here A13F 0.2D A6. Again the simple substitution methodology. For A it is represented, A is represented as 10, its value, 1 as it is, 3 as it is, F 15. Again D 13, A represented as 10. Here it is written the concerned digits, 10, 1, 3, 15, 2, 13, 10, 6. The idea here is we have to write this is the concerned hexadecimal digit. For the concerned hexadecimal digit, we have to write the 4-digit binary value. We can either directly take it from the table and write. Consider for 10, 1010, for 1, 0001, for 3, 0011, for 15, 1111. And again after fraction also we have to represent as it is only. For 2 0 0 1 0, here the decimal point can be represented. For 13 1101, for 10 1010, and for 6 0 110. Again when combining all the answers we can write here as 1010 0001 0011 1111 dot. Again writing all those answers 0010 1101 1010 and 0110 to the base of 2. So likewise we can able to substitute and find the binary value directly. When you call numbers, understand clearly now the idea. Okay, that's all for today's video. Keep supporting Sai Suriyas Academy. In my previous videos, in the number system conversion, other types of conversions has been taken. So if you want to check my number system conversion playlist. Okay, thank you. We had already discussed about so many types of conversions in the decimal, binary, hexa and octal. If you want, check my previous videos. It is given in the number conversion playlist. Okay, now moving on to today's topic. In today's video, we are going to discuss about octal to hexadecimal conversion and hexadecimal to octal conversion. The base idea here is we have to convert in octal to hexadecimal. We have to convert the octal into a binary. And from the binary, using the grouping method, we have to convert it into hexadecimal. And vice versa, same, the hexadecimal to octal also, the same method applied, but in the grouping method, the number of bits differs. Okay, now we can check one by one. We all knew that the octal consists of base 8 number system, which consists of digits only 0 to 7. 8 and 9 are not allowed here. Whereas in the hexadecimal, it consists of base 16. The digits from 0 to 15, and the digits from 10 to 15 is represented as alphabets A to F, and octal digit is always represented by 3 binary digits, whereas the hexa is represented by 4 binary digits. Here in the table we had given the hexa numbers starting from 0 to 15, and the concerned 4-bit binary digits is given here for your reference. It can be directly substituted. These values can be directly substituted. We can see in the examples. For hexa, it is represented as 4-bit binary. When considering for octal, the same 0 to 7 digits are used, but here only 3 binary digits are implemented or used here from this table. Okay, now move on to the first example. Consider in the first example, integer number that is without any fractional part, 365 to the base of 8. Here we want to convert this 365 to the hexadecimal conversion. First, what we are going to do is, we want to substitute the concerned binary values, that is the 3-bit binary values. 3 digit, not 3-bit, 3 digit. So 3, for 3 can be taken in the table as, consider the table. Here hexa value is given and the concerned binary value is given here. For considering octal, only 3 binary digits have to be used. So for considering 3, here it is given as 0011. We want only 3 binary digits. So 011. Here it is represented as 011. Similarly for 6, 110, it is substituted as 110. Similarly for 5, 101, it is represented as 101. So now the binary value is written as 011, 110, 101 to the base of 2. Now the binary value is formed. Again we want to calculate, or we want to convert it into the hexadecimal conversion. How the conversion takes place? Consider this number and we want to group the bits starting from the right to the left. Since it is an integer number, it can be done from the right to the left. So consider, here we want to, since we want to convert to hexadecimal, it is grouped as 4-digit binary. So the last 4 digits 0101, it is grouped here. Again, after the next 4 binary digits are 1111, which is grouped here. and at last we are left with only 1 zeros. In order to convert to hexadecimal, we have to add 3 zeros. 3 zeros can be added. That is, we are following the rule, but adding 0, since we are having 0 here, it doesn't have any value here. But according to rule, for converting to hexa, we are adding 3 zeros in the left side. Again, the values can be found for 0, 0, 0. The hexa value for 0, for the binary value full zeros, it is represented as 0. For 4 ones, it is represented as 15, the value, and the value 15 is represented as F. It is given here. And for 0, 1, 0, 1, the concerned hexa value is 5. So it can be written as, discarding this left hand side 0, F5 can be written, and this is the hexadecimal conversion. Now this is for the integer part. Now we have to calculate for a fractional part. How the grouping differs in the fractional part. Consider another example, 215.337. The concerned octal number have to be converted into hexadecimal. The base idea is here, by binary value substitution, 3-digit binary value, we are going to convert it into binary. So for 215.2, you can refer the table directly. So I am directly telling the values, the substitution values for 2, 0, 1, 0, for 1, 0, 0, 1, for 5, 1, 0, 1. Similarly for 3, 3, 7, the values are given here, and then the values are represented. That is, after decimal point also we are doing the same substitutions, and the values can be written after the decimal point. That is, for 215, 0, 1, 0, 0, 0, 1, 1, 0, 1 point. For 337, 0, 1, 1, 0, 1, 1, 1, 1, it is written. Now how the grouping differs means, this is the integer part and this is the fractional part. The same answer I had written here. So for the integer part, we have to group the bits into 4 digits, starting from the right to the left. But for the fractional part, we have to group the bits starting from the left to the right. So consider, starting from right to left, the first 4 digits is 1101. Again the next one is 1000. Again we are left with a single 0. In order to convert to hexa, we are simply adding 3 zeros. And then after the decimal point, we are dividing starting from the left to the right. So the first 4 bits are 0, 1, 1, 0. And then again 4 ones. Again we are left with 1 0. According to the rule, we can add 3 zeros at the end. So for converting to hexadecimal, we are adding 3 zeros. 1, 3 zeros. So now this 0 represents 0, and then this 1000 represents the value 8 here, and then 1101, which represents value 30 and the concerned alphabet D. For 0110, 6. Similarly for 111, the value is 15 and the alphabet is F. For 1000, we had added 3 zeros. So now the values become, for 1000, the concerned hexa value is 8 here. So it is written 8. So the final value is 8D.6F8. This is the concerned hexadecimal value. Now we are going to discuss about the hexadecimal to octal conversion. That is, from the 16 base, we are going to convert it into the octal base 8 number system. The difference is in the grouping system only, but the other procedures are as it is the same. So here, hexadecimal is always represented by a 4 binary digits. So for A, it is the value concerned, value is 10. For the alphabet A, 10. For 10, the value is 1010. It is written here. For 2, 0010. And then for B, the concerned number is 11. And for 11, the value is 1011. For A, 10, the value is 1010. For 6, 0110. And similarly for C, the concerned, for the alphabet C, the concerned value is, hexa value is 12, and the value is, binary value is 1100. Again, we are going to group these bits. Now we want for octal conversion. So the number of bits has to be divided into 3 binary digits. So for the integer values, we have to start from the right to the left. The values can be divided into 3 bits. And for the, after the decimal point, the fractional value, the values can be divided as 3 bits starting from the left to the right. So by dividing 011, 101, 0, 0, 0 and finally 1, 0, 1. Similarly, when dividing starting from the left to the right, we had got as 101, 001, 101 and 100. Here we have actually the correct 3 binary digits. When dividing these hexa values, we had already getting correct 3 binary digits. There is no leftover of a single digit or a double digit. So no zeros can be added or anything can be done. Directly we can substitute the octal values. So for 101, 5. For 0, 0, 0, 0. Similarly 1015, for 011 the value is 3. For 1015, for 001, 1. Similarly 1015 and 1004. The values after the decimal point can be written with the concerned decimal point followed. So the values can be written as 5053.5154. So no zeros are added here. Suppose if you are left over with a single binary digit or a double binary digit, we can add zeros here in the integer part as well as add zeros here in the fractional part. Since it is not needed, we had not added any zeros. Directly the values are grouped here and substituted and the concerned octal value is found and it is written here. Hope you can be clear with the both type of conversions. Now a small work for you. Convert 536.14 to the base of 8. Convert it into the hexadecimal conversion and write it in the comment section. Okay, that's all for today's video. Keep supporting Sai Suriyas Academy. Thank you. We'll meet you all in next video. Thank you.